Good evening. Today we will talk about the double integral in polar coordinates. Yet again an important topic for this class. So as you noticed, I already sketched a picture here, and you should do it on your own, on your notes, while I go over a couple of background information before we proceed with the topic at hand. A very important topic because, as you will see in many applications, the ability to compute these integrals in various coordinate systems like polar coordinates rather than Cartesian coordinates provides a big advantage in some cases. It all has to do with the shape of the domain, and with a little bit of practice it's pretty easy to realize when it's actually advantageous to use polar coordinates rather than Cartesian coordinates. So while you sketch this picture here, what I represent in this picture is basically the typical domain for which Fubini's theorem can be applied in polar coordinates. Because just like in the Cartesian coordinates, Fubini's theorem has some limitations. It cannot be applied for any domain. The domain needs to have a certain shape, although it's pretty general, and most of the problems you'll encounter can be solved via Fubini's theorem. So just a little bit of review. Remember the polar coordinates, the relationship between the polar coordinates and the Cartesian coordinates is the following one, right? So if you pick a point on the xy plane, P of coordinates xy, rather than using the Cartesian coordinates x and y, you could use the so-called polar radius, which is the length of the segment OP, and the angle measured counterclockwise from the positive semi-axis. So that also identifies the point. The whole thing is that as with any two-dimensional system, you need two pieces of information, two coordinates to identify the point. And so either the x and y or the radius, the polar radius and the polar angle. So of course, to be able to switch between the two coordinate systems, you need to know the relationship between these coordinates. And as you might remember from previous courses, x is, if you form a right triangle here, x is r cosine of theta and y is r sine of theta. But as you will see in this class, it's not just a matter of replacing x and y with r cosine and r sine. The dx dy changes in a slightly different way. It's not just dr d theta, and that's something that you have to remember. And also, of course, to make sure you write it correctly in your formula sheet. It's very useful to also know two related identities from these equations, namely that x squared plus y squared is r squared. If you square and add these two together, because sine squared plus cosine squared is 1, then you always have this substitution. So whenever you have the quantity x squared plus y squared, that can be replaced by r squared if you switch to polar coordinates. And that's an indication, right, that things can be easier via polar coordinates if you have quantities like this, because handling x squared plus y squared is harder than just r squared, right, as you'll see when the time comes to integrate. Might be also useful to remember that y over x is tangent of theta. That appears a little bit, less often in our applications, but these two are related to these substitutions from Cartesian to polar coordinates. All right, so the goal, like I said, is to start with a function, a double integral in Cartesian coordinates, and switch to an integral in polar coordinates. So that means you're going to have something like dr d theta, right? I mean an integral in terms of the new variables r and theta. So the domain that is suitable for the Fubini's theorem in polar coordinates has this generic shape. So just like the Fubini's theorem in the Cartesian coordinates, you have a requirement to have one of the variables between constant bounds and the other variable between bounds that can depend on the other variable. Although, as you will see in our homework, at least, I'll make it so that all bounds are constant, because just to make homework a little bit less involved. But generally speaking, this is the type of domain you would like to have in polar coordinates. And I'll explain that in a moment. Let me actually thicken the boundaries of this domain just to visualize it. Like that. Okay, and I have to make actually a pause because I'm out of ink here. Just a second. We'll continue on this page in a moment. All right, so this is the domain, and the reason it looks like that is because we make the polar angle the variable that denotes the polar angle theta to be between constant bounds. So let's say theta is between A and B. So A is the smaller angle, so take a look at this at the positive semi-axis, starting this little arrow here, starting from the positive semi-axis to the to this boundary on the this ray here that emanates from the origin, and then all the way counterclockwise to the other boundary corresponding to theta equals B. So basically the whole domain is inside an angle, in other words. Those are the, from your perspective, let's say the left and right, more or less, obviously, boundaries of the domain. And then from the center, from the origin, as you move to the right corner, then you have two other boundaries that can be actually generic functions of theta. A typical function in polar coordinates is given usually as a function for the polar radius. So this boundary here, let's say r, the variable that knows the polar radius, is between two bounds that can depend on theta. Let's say f of theta on the left side and g of theta. So that means this curve here is r equals f of theta, and this one here is r equals g of theta. Other than that, the whole concept of setting up the Riemann integral is exactly the same. Okay, so the partition process is the same. What is different is that the geometry is different, because the partition is not going to result in non-overlapping squares or rectangles. It will result in non-overlapping patches with two straight lines and two curves lines as boundaries, which can be approximated by circles if the partition is fine enough. More to the point, and let's try to do this without making too much of a mess, more to the point, and by the way, we're going to do this in a kind of using a shortcut, because we're not going to waste time to set up the whole Riemann sum in all the details, just like we did it in the case of Cartesian coordinates, because hopefully we know the drill by now. So remember, we take each domain starting with the constant bounds, and you make your partition. Remember, eventually the length of each segment in the partition is going to be shrink to 0, basically, right, as you take the limit of the Riemann sum. So in other words, delta theta is going to approach d theta, delta r is going to approach dr. So I'm not going to write the full Riemann sum. I'm going to just basically focus on what you actually integrate when you take the limit of the Riemann sum in polar coordinates. So as you make this partition, let's say somewhere in between here, one piece in that partition goes from, let's say, theta plus, excuse me, what do I say? Yeah, from theta to theta plus d theta, right? So what I want to emphasize is that the length of that partition is d theta, right? After you take that's kind of looks bad here. So the length of the partition is d theta, right? As you take the limit of the Riemann sum. And in the same manner, for every theta, so for a given theta, you look at the domain for r, which goes from f of theta to g of theta. You're going to partition this, and somewhere in the middle, you're going to have a typical segment in the partition from r to r plus dr, right? Again, the length of this partition will be dr after you take the limit of the Riemann sum. But the question is, how does that look like geometrically? And let's actually use a different color here to emphasize it. A small change, which is d theta, right? A small change in theta will result in a very thin angle somewhere in the middle here. So let's say, again, exaggerating the distance here, so it's visible, but just imagine this angle is really thin, right? So this corresponds to d theta, this angle. And if that angle is very, very thin, then the curves f of theta, g of theta can be approximated basically by arcs of a circle. So as you look at the partition corresponding to r, let's say somewhere here is r, that's going to be the portion of the curve resulting from that partition, approximated by a circle again. And then a small change in r results in a nearby arc very close to this guy with the radius r plus dr. So when we do the partition for this two-dimensional domain, again by r and by r and theta, the non-overlapping patches that will cover the domain are going to be in this shape. I mean, you can call them round rectangles, but of course they don't have a specific shape. Or more to the point, it's like the small segment of a circle between two circles, but in a very narrow angle. This is the point on the partition. This is where you pick a point, an intermediate point, you evaluate the function, and then construct the Riemann integral. Okay. Now the question is, remember, in the Riemann integral, let's change back to the regular color. In the Riemann integral in Cartesian coordinates, what we evaluate is the function evaluated at an intermediate point times the area of the patch. In the Cartesian coordinates, of course, that patch is in the form of a rectangle, so that's why it's dx times dy. All right. So obviously, when I move to polar coordinates, x and y are going to be replaced by r cosine, r sine. The question is, what is dA gonna be, right? I mean, what is the area of that patch? Because again, spoiler alert, is not going to be just dr d theta, because the shape of the patch is not a rectangle. Okay, that's the key thing. So how do we compute it? Well, again, the geometry comes to rescue here, because we know from the geometry, that if we have a segment of a circle, so let's say this is the angle theta and this is a radius, the area of a segment of a circle, or a pizza slice, if you feel so inclined, is going to be r squared times the angle in radians over 2, right? If theta is 2 pi, which is the full circle, that results in pi r squared, which hopefully you remember is the area of a circle. Now, in our case, going all the way back to this red patch, dA is going to be the difference between the area of two segments of a circle with the angle d theta, which is again a change in theta. So the wider angle is going to be r plus dr squared. That's the radius of the, not the wider angle, the larger segment of a circle. The radius is r plus dr. So we're going to square that times the angle, which is d theta, over 2, from which we subtract the smaller segment, which is r squared times d theta over 2. Again, this is kind of oversimplification, but in the end, that's what you will get when you take the limit of that Riemann sum. And this is what dA becomes. So let's do a little bit of computation here. We can factor d theta over 2. Square this expand this parenthesis, so it's r squared plus 2 r dr plus dr squared and then minus r squared. Okay, now r squared cancels. Dr squared can be neglected, can be approached to be zero. Basically, if you take the limit, if dr goes to zero, essentially the other higher order terms can be neglected in this approximation. So therefore dA becomes, if you simplify by 2, it becomes r dr d theta. Basically, in this approximation steps, the higher order terms of those terms that actually approach zero can be neglected because they won't affect essentially the overall limit. That's the whole idea. That's the reason you can drop this dr squared. When you take the Riemann sum, that piece won't affect the limit at all. All right, so now we're going to write the full formula on the next page. Remember, in Cartesian coordinates, dA is dx dy because it's just a square. In polar coordinates, this turns out to be r dr d theta. In the beginning, many people actually, not many, but some people in the beginning always forget this extra r, okay, if they rush. So don't forget this extra r because the extra r is part of dA, of the new dA in polar coordinates. So in a nutshell, you're going to replace x with r cosine, y with r sine, and finally dx dy with r dr d theta. So you have that extra r that you should not forget. So let's write down the formula on the next page, and then we're going to obviously finish up with examples. Okay, so Fubini's theorem in polar coordinates. So suppose my domain is given in polar coordinates with theta between a and b. So we're going to always have constant bounds for theta in our formula here. And then in general, r is allowed to be between bounds that may depend on theta, although in our applications they will be constant. But again, just to emphasize that they can be depend on theta. So with these notations, a double integral over this domain of some function h of xy dA is going to be the integral from a to b. So the outermost integral is always in terms of theta. And then the integral from f of theta, g of theta, of h evaluated at r cosine. So you're going to substitute x with r cosine, y with r sine of theta, and then r dr d theta. And without further ado, let's just go straight to a typical problem formulated in Cartesian coordinates, and then let's see how we can recognize it, if it's suitable to do it via polar coordinates. We're gonna, there's some sirens out. So we're gonna comment on how we can actually tell basically if it's worthwhile to do it via polar coordinates. So let's say I have to, let's say the problem states the following, okay? So find the integral of, the double integral of the function x minus 2y, where the domain D is the region in the positive quadrant of the plane, bounded by the circle, and that's a keyword to indicate that probably polar coordinates are the way to go. The circle x squared plus y squared equals 4, the lines x equals 0 and y equals x. Okay, let's actually do it directly in polar coordinates, and then we're gonna see how it may look like in Cartesian coordinates, just to see the difference. So if we sketch the domain, so it lives in the first quadrant, as the problem states, and the bounds are x equal, so first of all, the bounds are the circle of radius 4, but I'm gonna just sketch the, like that, the just the portion in the first quadrant. So the radius is 2, and then x equals 0, which is the y-axis. So let's emphasize this portion of the domain, and y equals x. So therefore, we're going to talk about this region over here. Okay, so if the domain is related to a circle, either a full circle or a segment of a circle, chances are, it's never a guarantee, but chances are polar coordinates make the problem much easier when it comes to integrating it. Right? So let's see, how do we describe the domain in polar coordinates now instead of Cartesian coordinates? Well, in polar coordinates, first of all, let's look at the bounds for theta. The lower bound for theta is actually 45 degrees, because this is y equals x, so that's the diagonal line. So the lower bound for theta is pi over 4, and the upper bound for theta goes all the way to 90 degrees, so that's pi over 2. Now for a typical theta, so again, if you imagine a typical ray like that, you have to look at the bounds for the radius. The radius in this case has constant bounds. It starts from 0 and goes all the way to the circle of radius 2. Again, it doesn't have to, it may depend on theta, but in this case the bounds for r are also constant. Okay, so now it's just a matter of replacing x and y with the polar coordinates. So the double integral in Cartesian coordinates becomes the integral from pi over 4 to pi over 2. Remember, always theta on the outside. And then from 0 to 2, x becomes r cosine of theta, minus 2r sine of theta, and dA, again remember, it's the extra r dr d theta. Innermost integral is always in terms of r, outermost integral in terms of theta. Now, without writing it down, look at this in this right corner here. I want to remind you that when you look at when we talked about the double integral over rectangles, if you have constant bounds everywhere, and you can integrate, if you integrate a product of a function in x and a function in y, doesn't matter whether it's x, y, or r theta. If you can separate what you have to integrate into a product in one variable versus the other variable, actually this simplifies into a product of integrals. In one variable times another simple integral in the other variable, like so. Okay, so this can be used here because at this point, of course, we know this does. I mean, the original domain is not a rectangle, obviously, but r with respect to theta, if you are to sketch them as Cartesian coordinates, they form a rectangle. So the point is that factorization that leads to a product of integrals still applies here. Again, people sometimes get confused because they don't see any theta, but 1 times d theta is the actual factor that depends on theta. So bottom line, this splits into a product of integrals. The integral in theta, which is just 1 times d theta, and the other integral, not just one, so sorry, I take it back. I was thinking about a different problem. Let me actually take a step back here. I had in mind the next example, sorry about that. Because there is sine of theta, cosine of theta. So let's backpedal just a little bit. So in this parenthesis, we can still apply the property that I was just talking about, right? When you split this into a product, but we need to do a little bit of algebra more here. So we can factor r in the parenthesis, and let's factor it on the right hand side. So you're left with cosine of theta minus 2 sine of theta, and then r combined with the existing r becomes r squared, dr d theta. Okay, so one more time, now splits into a product of integrals. The portion that depends on theta, which is cosine of theta minus 2 sine of theta. This is dr here. D theta times the integral that depends on r only, which is from 0 to 2, r squared and dr. So you could do both integral at the same step. All right, so the first antiderivative is sine of theta plus 2 cosine of theta between pi over 4, pi over 2. And then the other one is r third over 3 between 0 and 2. So let's plug it in. Sine pi over 2 plus 2 cosine of pi over 2. And then we're going to plug in pi over 4, like so. And then for r third over 3, that's 8 over 3 minus 0. Okay, so sine of pi over 2 is 1, this is 0, this is 1 over root 2, and this is again 1 over root 2, right? So what do we have here? We have 1, let's see, minus 3 over root 2 times 8 over 3. If we distribute that, that's 8 over 3 minus 8 over root 2. Let me see. Yeah, we'll just leave it at that. I mean, I guess we can multiply by root 2 here and write this as 8 over 3 minus 4 square root of 2. Right, we can leave it like that, or we can use the calculator, whichever you prefer. Okay, so that's a typical medium difficulty problem, basically, with polar coordinates. And actually, before we turn the page, you don't have to write this down, because I don't want to turn the page until I make the point how nice this transition to polar coordinates can be. I'm going to make a mess here on this page here, but hopefully you're not going to do the same on your own notes. I just want to show you how would you deal with this integral if you don't have polar coordinates, like if you don't use this transformation. Well, if you get stuck into Cartesian coordinates, let's change the color a little bit. So let's go back to the domain here. If I look at the domain, I can view this domain as a type 1 domain. So first of all, you're going to have to compute the x coordinate of, so the domain can be viewed between the circle and the line y equals x. So because you can view this as a type 1 domain in Cartesian coordinates, the top boundary of the domain here, that I write now in green, from the equation of the circle is going to be square root of 4 minus x squared, positive square root of 4 minus x squared. And then you're going to slice it vertically, here with green, a typical slice, and you're going to go by the x coordinate on the outside of the integral. But I need first to compute the intersection point between the line y equals x and the circle, so I can identify correctly the domain for x. So what is that intersection point? Well, on the circle when y equals x, if I replace y with x, and I do that computation here, square both sides, 2x squared equals 4, that makes x equals square root of 2, positive square root of 2, because we are in the first quadrant. So on the outside, using Fubini theorem, you're going to have the integral from 0 to square root of 2. On the inside, which is a real troublemaker, is the integral from the lower bound for y, which is on the line y equals x. So that's going to be x. And the upper bound is going to be square root of 4 minus x squared. And then the function to integrate is going to be x minus 2y, and then dy dx. So I don't know actually. So yeah, I mean, it's not going to be impossible. If you feel like it, as a practice, you could do it, or you could just feed it to Maple or Wolfram Alpha to convince yourself that you get the same answer, like the one down below. But clearly, the work is far longer in this case. First of all, notice that the establishing the bounds took a little bit longer. Secondly, this bound here on the innermost integral usually is bound to make, it's no pun intended, right? It's bound to make the second integral probably difficult, right? Because you're going to plug in that square root into whatever you get from the first integral. So once again, round domains typically look nicer when you set them up in polar coordinates. So let's move on with the next page for the next examples. Okay, so here's another favorite example of mine. Just as a trivia stuff, the integral of e to the x squared or e to the minus x squared in calculus 1, like that, are examples of integrals that cannot be computed in terms of elementary functions. In other words, you can approximate it via, say, series or stuff like that, but although the antiderivative exists, it cannot be given in terms of elementary functions, like polynomials, radicals, and so on. Or fundamental functions, like trig functions, natural logs, whatever you like, okay? So you cannot basically find the exact format for this antiderivative. However, as it turns out, and that's my second example, right, for today on the double integral, if the domain is suitable again, then we can easily compute, in fact, the double integral of the function, let's say e to the minus x squared minus y squared dA, which is kind of related to these calculus 1 integrals, right? And let's say for simplicity, let's say the domain is given between, well, let's actually, let me think a little bit. How do I formulate it? D is bounded by the circle x squared plus y squared equals 1, y equals x, and then y equals 0, and again, first quadrant in the positive region of the plane. Okay, so if I were to sketch this domain, it'll look like this, kind of similar to the one before, but in the lower portion of the xy plane here. So the radius is 1. This is y equals x, and of course y equals 0 is the x-axis. So 45 degrees, which means the bounds for the polar angle are between 0 now, starts from the positive semi-axis, all the way to pi over 4. And for any given theta, the bounds for the polar radius go from 0 to 1 on the circle. Now remember what I told you, that x squared plus y squared is r squared as soon as you move to polar coordinates. Now if you forget this fact, of course you can still get it, because if you plug in r cosine r sine into this expression over here, then you're going to get r squared. But it just saves some time, you know, if you remember that substitution. Okay, so then what does my double integral become? Well, again, that's the integral from 0 to pi over 4 on the outside, and from 0 to 1. And notice here that e to the minus x squared minus y squared, right? Because that, if you pull the minus out, is like this. That becomes e to the minus r squared, which would still be impossible to solve, but remember, dA contains that extra r when you switch to polar coordinates. And that extra r actually makes all the difference in my ability to, in fact, compute this integral. Okay, as I mentioned before, you can still split this into a product of two integrals, one in theta, which at this point in time only contains 1 times d theta, is just d theta basically in terms of theta, and the integral in r. And that extra r is useful because you can make a u substitution. So we can substitute minus r squared for u, and then du is minus 2r dr. The new bounds when r is 0, u equals 0, and when r is 1, u equals minus 1, in that order. The first integral, I hope you guys see it, is pretty straightforward, right? The integral of 1 d theta is just theta, evaluated between 0 and pi over 4. With a little bit of practice, people just write pi over 4 right away whenever they integrate d theta. And the integral in terms of r, I mean u now, because we made that u substitution, is from 0 to minus 1 of e to the u, r dr becomes du over minus 2. So pi over 4, and then let's integrate minus 1/2 e to the u between 0 and negative 1. So we'll plug in minus 1 first. So minus 1/2 e to the negative 1. And then we'll plug in 0 minus becomes plus, right? Minus 1/2. So plus 1/2. Okay, so if I pull 1/2 out, becomes pi over 8, and then 1 minus 1 over e. And that's the answer. So let's see, let's do one more example. I have some room here, but I won't do it right now because, I mean, I'm not going to do it here. I'm going to turn the page because I want more room for the last example. Let's just, for the sake of it, again, let's compare it with Cartesian coordinates. We're not going to solve it via Cartesian coordinates, but how do we deal with this if we didn't have the inspiration to set it up in polar coordinates? Well, once again, see, if you look actually in this case, you can view this as a type 2 domain. In other words, we can slice the domain horizontally. Let's again change the color just to emphasize. So look at the typical horizontal slice with the bounds for y on the outside. Once again, we need to figure out the bounds from that intersection. So the intersection between the circle and the y equals x. Okay, so y equals x intersected with the circle. If y equals x, that becomes 2y squared equals 1, and y equals 1 over root 2, or square root of 2 over 2. So the bounds for y on the outside will be a 0 and 1 over root 2. Then we're going to have to write the bounds for x in terms of y. The lower bound for x is just y, obviously, and then the upper bound comes from the equation of the circle, which is square root of 1 minus y squared. So once again, in Cartesian coordinates, the same integral will be from 0 to 1 over root 2, then from y to square root of 1 minus 1 y squared, e to the minus x squared minus y squared, and then dx, that's the innermost integral, and dy. So the problem is that you still cannot solve it, right? It's not that it's harder set up, but it's actually, again, impossible, because, again, we cannot integrate this as it is. There's no way to make a u substitution now. See, for example, you can pull out e to the minus x minus y squared from the innermost integral, but you're still dealing with an antiderivative which we cannot compute explicitly. So again, I found that interesting that just moving to a different coordinate system, it becomes a straightforward problem, and we can find the explicit solution in that case. So let's stay tuned for the last example on the next page. All right, so we talked about this example or something similar to it. We talked about this before, right, in the previous lesson. So this is kind of the trickiest type. I mean, not the tricky. It's kind of like the most difficult type of problem because you really have to go slow to visualize carefully the object, and most importantly, to identify correctly the actual domain of integration. So here we need to find the volume between two surfaces. That relates to the double integral because remember, the if you have a solid defined as z between two surfaces, like so, given the default meaning of the double integral, that volume is simply the double integral over the top surface minus the bottom surface over the common domain. See, this is the common domain here. It's people what people kind of get confused usually. But intuitively, basically, if you look from above, I'm going to put this in quotation marks because it doesn't have to be just along the z-axis, but because it's along the z-axis, it's like you look it from above, then you're going to see the domain D projected in the xy plane. Rather, you're going to see this, I should say, you're going to see the surfaces, not the domain, you're going to see the surface projected in the xy plane, projected in the domain D in the xy plane. So in this case, we're dealing with paraboloids, right? We like I said, we had this sketch before, so you may want to take a look at the last part of the previous lesson. But if you were to sketch the picture here, let's see if we could do a good enough picture here. We're going to have the bottom of, this looks like a Kinder egg basically, right? You have the bottom portion of the object, which is the paraboloid open upward, like that. And then intersected with the top portion, which is the paraboloid open downward, like this. Right? Again, I'm exaggerating the shapes a little bit. Right? So wherever they intersect, in this case, and we're going to have to compute that intersection between the two, that is the common domain. I mean, that's gonna be the stuff that projects onto the common domain. So if you see it from above, right, where my arrow is there. All right, so intuitively, if I see it from above, both surfaces are going to be projected onto whatever this intersection is in the xy plane. So if I look at it from above, this intersection, which is going to be a circle, as you'll see in a moment, is going to project onto the common domain. So let's actually use a different color here for the common domain. That's the common domain of the top portion and the bottom portion of the object. Okay, so the top is z equals 12 minus 2x squared minus y squared, and the bottom portion is z equals x squared plus 2y squared. And the volume is the double integral over the domain D. So your job is basically to figure out the shape of that domain. Now again, remember the shape of the domain comes from the intersection between these. So how do you intersect them? You're going to solve as a system and eliminate z, because you need to figure out the relationship between x and y. That's what gives you the equation of the domain, or the description of the domain. Actually, when you do the intersection, you're going to find the boundary of the domain, because obviously the surfaces project not just on the boundary of that domain, but also on the inside. It's going to be a disk, not just a circle. So when I set this equal to each other, I made it so that the numbers look nice. Move everything to the right hand side. That's 3x squared plus 3y squared equals 12. Divide by 3. That gives me x squared plus y squared equals 4. So notice how patient you should be before you actually set up the integral. You shouldn't rush on this until you're very sure what you're doing. So now you can take it separately just to see it better. So I can visualize the domain, and it turns out to be a circle of radius 2. Okay. Now we can proceed with setting up the integral. So it's going to be the double integral over the common domain, top surface 12 minus 2x squared minus y squared, minus bottom surface x squared plus 2y squared dA. That's the double integral in Cartesian coordinates that I need to solve. Simplify this a little bit. That's minus 3x squared minus 3y squared. If we pull out the 3, which further emphasizes the appropriateness of the polar coordinates, so the stuff to integrate is 12 minus 3 quantity x squared plus y squared dA. Clearly, looking at the domain and looking at the function to integrate, the polar coordinates are the way to go. Now, what is the domain what is D in polar coordinates? Well, it's a full circle, so the polar angle is between 0 and 2 pi. And the polar radius is from 0 to 2. So the outermost integral runs from 0 to 2 pi, innermost from 0 to 2, 12 minus 3r squared, right? X squared plus r squared plus y squared becomes r squared. And of course, don't forget the extra r that comes from dA. Okay, so a little bit of algebra more. Here 12r minus 3r third dr d theta. And this again splits, hopefully you know the drill now, into a simple integral in theta and an integral in r. The integral in theta is just 1 d theta, so that's theta between 2 pi and 0, so that becomes 2 pi. And then the antiderivative in r, that's 6r squared minus 3 over 4 r4 between 0 and 2. 2 pi, we're going to plug in 2, that makes it 6 times 4, that's 24. 3 over 4 times 2 to the 4, which is 16, and minus 0. It's 24 minus 12, which is 12, and then the final answer is 24 pi. All right, so I think that is enough. Next time we're going to talk about, I think, some applications of double integral, like the center of mass, before we move with other topics like the surface area, and then finally the triple integral, which is the last, I think, portion of this unit. All right, I'll see you next time.